am one very determined person. I've been working with quality control for over 50 years. When I say going back to those small labs, it was a long time ago. And we had a batch of problems that needed to be solved. And those problems have changed remarkably little over some 50 years. And I've come to the conclusion that the only way to solve those problems is to computerize the solution. It was largely computers that created the problem, and computers are going to create the solution, especially now with AI. I had envisioned AI and what we're doing now 20 to 30 years ago, saying, I want people to be able to go into this software and say, tell me more, show me an example, make this clear to me. And now with the power of AI, we're able to do that. Almost. We're getting there. What we're going to do today, and guys, just jump in if you've got a question anywhere. We're going to go through a brief educational session, which is actually a preview to an online course. I had hoped to have the course ready to show you today, but we're still in some technical setup processes. What I'm using for my online courses is the same educational platform that they used at Rutgers University. It's called Moodle. It's an extremely powerful educational platform. It gives you time for guided discussions. You can, we're now able to create little calculators for you to use. And I really enjoy using that. And more importantly, it lets you do quizzes to make sure that people understand what's going on. So we're going to go through what that course will introduce you to and just the high levels of that. Talk about points to ponder. Is it a safer world everywhere except LabQC? Ask you about the restraining forces. What would stop you moving forward with a new process? Because this is really the first big change in quality control in the past 50 years, really, since Westgard rules. And then we'll end up, of course, with more discussions. To begin with, we're going to look at what's going to happen in the online course, which is elevating statistical QC to clinical risk management. The first part of the course goes through an understanding of Westgard rules and Six Sigma through their common ancestor of Gaussian distribution. After that, there are 3 segments on why you can't evaluate acceptability of patient risk with sigma metrics, total error, or just looking at QC charts. And then we're going to look at this new process of M.O.R.E quality, and the M.O.R.E stands for mathematically optimized risk evaluation, a new process to evaluate acceptability of patient risk. Okay, in our new online course, so there will be 5 or 6 segments to this course. The first one is understanding Westgard rules and Six Sigma through their common ancestor, Gaussian distribution. What most of us are taught and have been taught for the last 50 years are these numbers. 68% fall within 1 SD, 95 within 2 SD, and 100% within 3 SD. And that's about all we're taught. We're not taught how that relates to what you're doing on a daily basis. And it really is the underpinning of everything that you're doing when you're evaluating quality control. If you're looking to evaluate analytical process quality, which determines the current risk, how many errors am I producing on a regular basis today, that's governed by the method accuracy, the method precision, and the standards that you set, the true value, the allowable error limit, and the current acceptable risk level. How many errors are you willing to report every year? The daily QC effectiveness determines the potential risk. If this was to fail, if the analytical process fails, what is the potential for reporting errors? And that's driven by the QC chart mean in SD, the QC chart rule, and the acceptable risk you want to set here. What people have been doing is they've been setting a sigma value or doing total error to say this is when my analytical process is acceptable. Sigma is the z-value from the mean to the nearest allowable error limit, the number of SDs from the mean to failure. The SDI is what you use on your daily QC chart. It's also a z-value, but it's from the mean to a specific point on the QC curve. The number of SDs from the prior mean to the current point. So this looks at one point. This looks at your overall method, accuracy, and precision. You know, this thing doesn't have a name. When you see in so many publications the distribution of data against your true value and allowable error limit, so I'm calling it a risk distribution chart. A z-value of 1 here means that 38 or 32% of values above this point are outside the curve. So if something falls outside 1 SD, 37% of your or 32% of your results will fall there. If it falls outside 2 SD, 2.3% of values will fail. There are all sorts of numbers. You can decide what z-value to use if you want to know the percent of values outside one side of the curve. So if I want to know when there's a 25% probability of failure, or a 10% or 5% or 1%, you can calculate all of these. This is your 3 sigma, which is equivalent to 0.135% of results falling outside the curve. If you start here, where your mean is in the center, you shift by 1 SD, you can see that only a few points are outside your, or remain, sorry, these points fall outside. The ones in between the blue and the orange are outside the original curve. These ones in the middle are inside both populations. If you shift 2 SDs, there's less of an overlap between the two populations. And if you shift 3 SDs, there's very little overlap between the two populations. So it's easier to tell if your mean shifts by 3 SD over here. Now there's a very small probability that the results from the shift of 3 SD are going to fall inside your previous limits. Got that? Anybody got questions? Is this just review of what you already know? Okay, I'm going to just jump on, because if you guys have a question or comment, just shout. QC charts work exactly the same way. All they've done is turn that Gaussian curve on its side. So you expect 68% of results to fall within plus or minus 1 standard deviation. If you pick a QC curve off of your computer, off of the wall, wherever your QC charts are, and you look back at 20 data points, you expect to see 14 of them within plus or minus 1 SD. You expect to see 2 or 3 of those 20 between 1 and 2 SD, and 1 out of 20 either above or below the 2 SD limit. If you shift by 2 standard deviations, 50% of the results will fall within your previous 2 SD range. So if you're using a 1-2S rule, you might fall out on the first run, you might fall out on the second run. You probably will not fall out on both of those QC runs. If you shift by 3 SD, then 17 of those 20 will be above the 2SD. And if you only see 3 results within your plus or minus 2SD, then you know for sure there's been a significant shift in the mean. So QC rules tell you if where you are has changed. They cannot detect a failure in a method that has already failed. So if you're not asking, is this method okay to begin with, the QC rule cannot tell you it has failed if it's already failed. One thing that we will never do is give you a QC process for a method that is already unacceptable. The margin for error, the number of standard deviations you can move before you're in trouble, tells you the size of shift you need to detect. If you need to detect a shift of 2SD and you're trying to do it with a 1,3S rule, then only 3 of 20 results will fall outside your 1,3S rule. The odds of you detecting that are very, very slim in one run. And it's understanding this Gaussian distribution that helps you understand how QC rules work. QC rules, everything in QC assumes you're dealing with Gaussian data, but you're often not dealing with Gaussian distribution. This is one of the samples that we're dealing with in one of our beta clients. This is their AST. They start in the month of January here, and as they proceeded into February, it looks like there was a significant shift down and then back up again. So you have 1, 2, 3 distinct populations. If you lump these all together, your QC rules and everything that you do, if you try to fit this into one data population, it simply is untrue. And everything that you assume about Gaussian distribution goes out the window. The first thing you've got to answer is it really one single population? I'm going to go back up here for a sec. The first data set here is from the end of January, and then the second one starts in the 1st of February. If I go down and I plot this not against the mean in SD that the lab has happened to set, but against the true value and allowable error limit, there really was not a shift in the mean between the start of the end of the previous month and the start of this month. The only shift that occurred was a significant shift upward that actually made the method better, and that occurred in about the 12th of February. So when they looked at their QC chart, they saw this shift up, and they got all of these QC flags. If they had asked the question, is this shift acceptable, they would have seen that this was actually a shift for the better. So QC rule flags do not tell you if the change identified is acceptable or unacceptable, if it's for the better or for the worse. So this is that risk distribution graph I was talking about, and this is part of the new software and part of what you'll see in the educational course. So this takes your data and says, here's where you were at the end of the prior month, here's where you were at the beginning of this month, here's what happened when you introduced a new reagent lot. What we do is we take the first 4 points from that new reagent lot and calculate the mean value, then say what is the usual CV or SD for this movement, for this method. So based on those first 4 points with that reagent lot, we project that you're going to be here. What actually happened is we were fairly close on where the mean was, but the standard deviation changed with that new reagent lot. However, if you failed, you would be down here. So you can see that although this method has a relatively high standard deviation, it's still within the allowable error limits, which are at the extremes of this red line. So this brings the two components together. This looks at the analytical process where the daily QC chart or the risk modification chart shows you has a single point changed. This tells you has the overall method changed. A quick review of the history and meaning of Six Sigma. Six Sigma started in 1987, many years ago. And they asked themselves, they did no quality control whatsoever. They were producing pagers. Remember pagers that you wore on your belt and they beeped if you had a message from somebody? Mm-hmm. And they just looked at how many pagers were returned by customers because they didn't work. And they said, well, let's assume that they didn't work because something was too big or something was too small. So we assumed there were two types of faults and that we had Gaussian distribution in our manufacturing process. They said if the method was 6 SD from the target, from the where we want it to be to the failure limit, even if it shifted 1.5 SDs, 3.4 defective pagers per million pagers produced. And they produced millions of pagers every year. So that's how Six Sigma came into being. And then they brought it over into medical labs. And I once saw an article written that said, by convention established before Six Sigma came to medical labs, we subtract 1.5 SD. It has nothing to do with what happens in medical labs. There is not one shred of evidence that I've ever seen that shows that the frequency of lab errors changes by 1.5 sigma over time. As a matter of fact, in those 6 labs that I monitored for 10 years, that definitely did not occur. So 2 things happen. That 1.5 SD shift does not happen in medical labs. There's no reason to apply it. And labs do not produce 1 million patient samples per year. If you were doing that, and maybe Dr. Peter, you you produce 2,740 patient results per day? I've seen labs that turn out that many, like sodium results. But unless you're producing that many patient results per day, a sigma value is pretty meaningless. If you only produce 100 patient results a day, it's going to take you 27 years to hit that 1 million results produced. So let's go back to Gaussian distribution. Sigma is the z-value, the number of SD from the mean to a point on the curve, and that determines the number of points that will exceed this allowable error limit. So your sigma value is a z-value from the mean to the allowable error limit. If your sigma value is 2 standard deviations, is 2, then 2.3% of results will fail. So your sigma is nothing but a z-value from your mean to your closest allowable error limit. Let's look at it from a more practical perspective. Let's look at the cliff of extreme risk. You don't care about Gaussian distribution. You don't care much about statistics. What you care about are patients. And you use quality control as a surrogate sample to tell you what's happening with all of those patients you report every year. If these patients were to shift by 6 standard deviations, then 50% of them would fall over the cliff of extreme risk, and some of them would face extreme harm. Your job, by measuring the controls that form surrogates for these patients, is to make sure that no more than an acceptable number go over the cliff. You can set that acceptable number at 3 sigma, which means you're going to allow 49 patients to go over the cliff every year, or you can set that acceptable risk at 1 medically unreliable result per year, and then you just back calculate what the sigma value must be. If you're willing to say, I'm willing to accept a total error and calculate my total error as the mean plus 2 SD, then you're willing to put 2.3% of your patients over the cliff. It's just a matter of looking, instead of what do these statistics mean, at what do these statistics mean to your patients. So why not set your acceptable risk at 1 medically unreliable result per year? When we look at QC from different labs, we see that about 80% to 90% of methods are already producing less than 1 error a year. Most methods produce less than 1 error every 25 years. So it's time for us to stop teaching things like 3 sigma is acceptable or 4 sigma is acceptable. What's acceptable is a clinical decision. How many patients am I willing to harm? If you're only testing 10 patients a day, you can move closer to that cliff and still only put 1 person over per year. Sigma completely disregards the number of patients that you test every year. Anybody got any questions or comments on that? Did it make sense? Going once, twice, 3 times.
It made sense to me, but I've seen some of this before, obviously.
Okay.
It makes sense to me as well.
Good. Okay. Did I spend too much time on it? Did it make too much sense? Or is that something that would help? Because this is what I'm going to be putting into that course.
Yeah.
I think it's a really helpful way of visualizing the different ways of thinking about risk.
Yeah. My first conversation I ever had with Dr. Westgard was about the calculation of critical systematic error, where he subtracts 1.65 SD. And the first thing I ever asked him is, why subtract 1.65 SD? And he said, oh, well, that's so no more than 5% of results fail. And I walked away, and it was like 6 months later that I finally realized what that 1.65 SD meant. And I think people don't understand that when they see that 1.65 SD in a formula, people are telling them it's acceptable to report a 5% error rate. And there's no way it should be acceptable to report 1 out of every 20 patients incorrectly. And when you see that 1.65 SD anywhere in any formula, that's what they're saying. They're saying 5% can fail. This, you've heard me talk about this too. At the least, the ability of QC procedures to detect medically allowable errors should be evaluated, and that your QA, your quality assurance, is used to determine if the quality activities you have put in place are actually working. There's a job, Dr. Peter, for your quality and compliance people. So answer this for me, please. And I know we've only got the 2 of you here, so just answer out loud. What do you do now? Do you calculate sigma for all of your methods? Do you calculate total error? Do you just look at the QC charts? Or are you setting an acceptable medically unreliable results?
We're not setting a medically unreliable result yet. We're probably at B or C.
Okay, a sigma method of greater than 2 or greater than 3. But you calculate sigmas.
Yes.
Yeah. And we'll get into how to calculate those things a little later too. Denise, what do you do? I think you're total error, don't you?
We're total error, yeah.
And 1.65 SD or 2 SD?
2.
2. So that's better than 1.65. But with 1.65 or with 2 SD, you're still saying I'm willing to accept a 2.3% error rate every year.
Right.
And there are some analytes, your cardiac markers, HIVs, a host of things you can think of that, perhaps your medical staff, if you look at that from a clinical point of view, it makes more sense to set it at the number of medically unreliable results per year. So the next part of the course is to say why you can't evaluate acceptability of patient risk with sigma, total error, or just looking at QC charts. Do you calculate it with percents or with units of measure?
Percents usually.
Percents, okay. This is going to be fun. Okay, sigma metrics first. Sigma and total error have assumed acceptable risk levels. Sigma metrics are misleading or inaccurate. If you ever look at sigma studies and they've averaged the sigma values, I saw software once that recommended a QC strategy based on the average sigma for your two controls. And because sigma metrics are not logarithmical, they're Gaussian in their distribution, but you sure cannot average them, and there's a poster I'll show you about that. Sigma and total error are misleading if you calculate them from percent bias and percent CV instead of units of measure. Dr. Peter, do you use percents or units to calculate your sigmas?
We use percent.
Okay, we're going to have fun with you too then. Okay, and sigma is hard-coded to report errors per million. So if you're reporting 100 samples a day, how many errors every 27 years? That's not a metric that any reasonable person would make up. So these are hundreds of sigma values from 3 different labs. This one has a sigma of 0.83 and reported 729 errors per year. This is a sigma of 1 and reports 3,000 errors per year. This is a sigma of 0.95 and reports 5,000 errors per year. Some of these labs report about 150 patients per day. Some of them produce 10 patients results per day, and some produce 30. So sigma does not in any way let you compare the number of errors produced. The correlation coefficient between sigma and the number of errors produced is 0.18. So there is like little to no correlation between sigma and the number of errors produced unless you're always reporting exactly the same number of patients from every analytical process. You're better to just go beyond sigma and tell people how many errors you're producing. A problem one of the reasons, another reason you run into that you can't just look at QC charts, this one I think you've seen before. This has to do with selecting QC rules based on sigma limits and selecting Westgard rules instead of selecting a rule that is guaranteed to detect 1 error per failure. So we started out with about 242 samples in the month, and we said, or per month, we said they reported 40,000 patient errors in the year and tested just under 30,000 QC samples. If they selected Westgard rules based on sigma values, that did nothing to reduce the number of errors produced or the number of samples tested. If we increase the frequency of controls based on sigma recommendations from Westgard, we used more controls, but it did very little to reduce the number of errors produced. What made a big difference was assigning the QC chart values to recent measured values. They seem to forget that when they're training people in quality control. Measure the mean in SD, put it on the QC chart. People like to pick and choose QC chart means in SDs from all sorts of different places. Then the software guided them to improve bias and/or precision. That again cut the number of errors in half. So now we've cut the number of errors from over 40,000 to down well below 5,000, or in the realm of 5,000. But with Westgard rules, you're still producing 5,000 errors per year. If you select the EQC rule, you cut that down even further. And if you want to get down to 0 errors produced, you have to bracket your quality control, which means doubling your QC. But you get to set the standard. Do you want to produce 0 errors per year, 5,000 errors per year, or are you happy up here at 40,000? And the thing about this is it helps to measure. It helps to quantify the number of errors you're producing. Right now, we just assume that the QC works, and it most often does not. Okay, why do QC rules not work? The effectiveness of QC rules is governed by the relationship between the measured mean in SD and the values you put on the QC chart. This is a preview of a calculator that will be part of the online course, and you enter the measured mean, the chart mean, the measured SD, the chart SD. What rule are you intending to use? And it will tell you that the chart SD is assigned so many SD above or below the measured mean. The chart SD is so many times the measured SD. So a positive flag will occur at 108, a negative flag will occur at 92. Where you think you're using a 1-2S rule, you're actually using a 1-4S rule. Now, question, guys. Software tends to come out looking like this, with little tiny gray print on gray backgrounds. I like to look at things that look like this. If we're creating QC software, would you like to see it in large, clear fonts or in this more artistic looking font? Am I the only one that this bothers? Or what would you like to see in your new software you're going to be using? Do you want the fonts to be large and bold? Do you want the fonts to be gray and gentle on your eyes?
Gray and gentle on the eyes.
Okay, good to know. Denise?
I think I can adjust to either way. I think it's helpful when the information that is provided after you enter yours that's like actionable, like this is a change that I need to make, that stands out in a more significant way.
Okay,
Cool.
Good advice. And I think the gray and gentle can be in a little larger font, and then maybe everybody be happy. And make sure that what your the meaningful information jumps out. So this is your baseline. And right now, I've set the chart mean at the actual value. I've set the chart SD at the actual value. I'm going to use a 1-2S rule. And this is actually a 1-2S rule. If I change my chart mean to 101 and I double my standard deviation, then I'm no longer using a 1-2S rule. I'm using a 1-4.5 at the high level and a 3.5 at the low level. If I change it so that I assign my mean at 99, now I'm using a 3.5 at the high level and a 4.5 at the low level. Now, and you see this happen, I've set my standard deviation lower than it actually is. I actually saw people do this thinking they would improve the method standard deviation by making it lower on the QC chart. Now you're using a 1.5S rule. And over here, and this is not uncommon, you're using a 1.6 rule or a 1.10S rule. Denise, this is what your QC looks like from January. So we calculate the actual rule that you're using. And as a positive rule, some of them go up above a 110X. Many of them, what you think is a 1.3S, is more than a 1.5S. As a matter of fact, the majority of your 1.3S rules are higher than a 1.5S, and the same at the low end. But these guys, you're using less than a 1.3S rule. So you're going to get more flags here. Here, you're using less than a 1.3S rule. So is this a real problem? Yes, it is. We see this over and over and over and over again for years. Every time I look at people's QC, they're not using the rules they think they are. And that's what Westgard said to me way back when. I said, we're putting the standard deviations from our proficiency program on our QC chart. What do you think of that? And he said, I think it's dangerous because you're using the wrong rule. So the effectiveness of your QC is governed by the QC rule you actually use and the margin for error to your potential acceptable risk level. So how many SDs can it shift before more than one error per day is reported? And again, this is your data. Most of them can shift. The ME to PARL varies with the acceptable number of M.O.R.E per QC failure and the patient volume. This red line is the margin for error that's required for you to use nothing but a 2.5S rule. So the vast majority of your methods are capable of reporting only one error per failure if you set the mean in SD correctly and use a 2.5S rule. And there's tricks to setting a 2.5S and convincing your software and your staff that they're using a 1.3S. So look beyond the statistics to what's actually happening. This goes back to your bias. So bias and standard deviation combine to create total error. If you think your total error is calculated at plus 2 SD, it's here at plus 1.65 SD, and this is where your data really are. Average sigma, you can't average sigmas. So if you have a sigma of 6 and another one of 3, if you average the sigmas, they're 4.5. If you average the numbers, the average number of errors is 675 errors per year, which is a sigma of 3.2, not 4.5. So if you ever see a study with an average sigma in it, just cross it out, it's useless. Okay, calculating from percent. If you calculate from percent instead of units of value, you get a different sigma and you get a different total error. So this has a measured mean of 100. The true is 100. The bias here is 0. How did you calculate it? The medical goal is 12. The standard deviation is 2. My sigma value is the total allowable error minus the bias divided by the SD. If bias is 0, the sigma will come out to 6, and the total error comes out as 4% of the true value. However, if I change that measured mean to 106, if I use units of measure to calculate, I get a sigma value of 3.0, and I get a total error of 10, which is 10% of the true value of 100. If I calculate from percents, I think my sigma is 3.2 or 3.18, and that my total error is 9.8. So if you're saying I'm going to say a sigma above 3 is acceptable, and anything 3 or lower I'm going to act on. You calculate from percent, you're good. Calculate from units, you're not good. Same thing with total error. My total error could be, if I want my total error to be less than 10. If I have a negative bias, now my sigma goes down to 2.82. I think this method is unacceptable. It still has a sigma of 3. I think my total error is 10.3%. It's 10%. So these formulas are not interchangeable. I actually did a poster called the sigma formula that Westgard uses is wrong, and it was published and presented because he encourages people to calculate from percent. To calculate from percent, you get a number that is different from the one that if you calculate from units of measure, they can't both be right. Again, let the software do it. Why should labs accept 3 sigma? There's no reason in the world, except the only one I've seen is, well, all labs were able to make 3 sigma. That's not a good reason, So the next thing we do in this online course is go through the process of mathematically, and the same with your QC chart review. There's no point looking at QC charts because generally speaking, the rules are all set wrong and you're not seeing what you should be seeing. And the chart only tells you the method has changed. Doesn't tell you if the change is for the better, for the worse, acceptable or unacceptable. If you upgrade to mathematically optimized risk evaluation, you get a very different picture. I'm not going to read these to you. I'll send them out in a handout. There are different building blocks. I'm not going to read this by any stretch of the imagination. I'll send this out to you as a handout, and there's just a very unique difference between the old and the new. And our challenge is to create this paradigm shift. Here we are, a very few people, but we're seeing what can be done. In the old process, risk is not measured specifically. Westgard QC rules are traditionally designed to detect failure levels of 5%. Look at it from a clinical perspective and do things differently. Work with computer designed single rules. So all your staff need to know is one rule. It's called a stop and act rule. When you get this rule failure, you stop and you act. And then the computer guides them in what to do, how to act, how to record it, takes them through a flow chart of what to do. Replace your Levy-Jennings chart with a risk variation chart. Did the method change? With a risk evaluation chart. Did the method change unacceptably? And the risk distribution chart. How far can the mean shift before failure? So we can do better than we've done over the last 50 years. When more quality goes up, patient harm goes down, and healthcare reduces their costs, saves time, money, and frustration. You start with a risk estimation, how much risk exists. You do a risk evaluation. Is that amount of risk acceptable? And acceptable risk is not a statistic. It's something that's acceptable to patients, physicians, institutions, and society. There are 2 components to the QC process. You can combine those 2 components into a single risk-based quality grade. And with those risk-based quality grades, you can pinpoint the methods that need attention and the attention that they need. So you can look, Dr. Peter, over those 5 labs and say, boom, here's the ones I need to look at, and here's what I need to do. Elevate QC is the company that's going to bring this software to life, following a process where you evaluate the analytical process quality. Where are you now? Then you optimize method accuracy or precision. design a QC process that is verified to detect failure in a single run. We have computer-directed processes to help troubleshoot when failures occur mid-month. We quantify the reduction in patient errors and QC flags. I've got a lab now, they're running 18% QC flags. With this method, you run less than 1% QC flags. And then you document the process so you can hand it over to your regulatory providers. So points to ponder. Everything else has got better, and we've stalled back here. How on earth do we make this change happen, is the question. And that's the next question. You can see that patient risk goes down, lab time and costs go down when risk management goes up. All of these good things happen. You get a lower number of QC tests, you reduce the QC runs, you get clear language, simple graphics, it's good stuff, but why would this be challenging to yourself or others? And Denise and Dr. Peter, can you just discuss this for a second?
Let's see. I'm tempted to see H right now because this is very revolutionary stuff. And it's hard to know, like, to me, what I'd like to hear this lecture, if you like, this webinar, along with the slides, and go over it a couple of times until I can go all the way through it and stay with you.
And that's the purpose of the course.
Yeah.
And that's what's going to be coming out by this time next month.
I think that'll be really helpful to have like a course, something that you can keep referring back to. And also, for me personally, with my learning style, like using real data, like you and I have been doing with John, and just seeing how it actually works with real data sets. That is super helpful to me because, when I was learning QC in school, it's just too generalized. It's not, specific enough to what we're dealing with on the bench in real time.
Yeah.
Amen.
Yes, right. Yes. And that's why two things that I'm trying to do. In the courses, you have calculators. So in those calculators, you can plug in your values and say what's happening with my stuff. And also in the in the software, it will model all of that for you. And in the courses, there are discussion forums. So what you'll have to do is you'll have to go in and create an example and then go into the discussion forum and discuss that example with other students in the course. So it makes sure that you understand it and that you communicate with other people and get their feedback on things and learn from other people's examples as well as your own. So I think those educational courses are going to be the key to moving this forward. It's just getting people to engage with the educational courses becomes the next problem. But that's, once they exist, then we have the solution in our hands with that and the software. John, do you want to speak to the early adopter program?
Yeah, thanks for that, Billy. As you all know, LabLogic QC, we're dedicated to helping labs to minimize these medically unreliable results, and that reducing the patient risk, and also cuts down wastage in the form of false QC flags. But we're very excited to announce that what we have is an early adopter program, and this is a focused group, invitation, application, limited number, and we're going to give early access to the software with support for anybody who's qualifying. This early adopter program, we've got the application process so that we can identify labs that best fit the criteria that will, and actually the best benefit from our approach. And the accepted labs will have a free 3-month review of their data. Then you'll be able to experience the software, experience the overall process firsthand. You have the option then to continue to a discounted rate, and that'll be ongoing then for the life of the product. This is definitely the future of QC. This is where everything has to head, because this is where the improvements can be made. And we also want to support any collaborations or any case studies for conferences and these kind of things. We've only got a limited number of spaces, so if you are interested, do please reach out and let us know.
I think one of the things that'll really help in the early adopter program, if some of us, the people participating, will know the value of it, but then we'll have to kind of sell that value to our senior leadership so that they will, support us in deciding to take it on as a paid resource for the continuing beyond the early adopters. So help with that, I think, would be really valuable for you all.
Yeah, so some sort of like statement of sort of the proof of the concept, sort of
right.
using your data. Yeah.
Even like how much money this is going to save in medically unreliable results, like if there's some way to quantify that.
Yeah, we can do that.
The goal is going to be to make sure that we have found out from you what will be relevant to the person you need to convince. That is going to be key.
Definitely.
Okay.
Exactly. And that's where having those metrics of, how many QC flags are you seeing now? So we're looking at the daily QC data now. We started this just looking at monthly QC means and SDs and assuming the data were Gaussian. And then we discovered that the data are not Gaussian. We were getting mixed populations and saying there was a problem with precision when there was no problem with precision. What there was 2 perfectly acceptable sets of data. So now we look at the detailed data, but we do it as a weekly look back, not as a actual live daily QC program. But we can help you with that weekly supervisory review of your QC. Send that up to us. We look through it and we can identify places where there is or isn't a problem and see where shifts occurred. And then the other thing we want to do, so we look back and say, did that happen? But we want to help you with SOPs to avoid QC flags. So to standardize processes for calibration verification and new QC lot verification, so that we can cut that number of QC flags. So you should be able to go to the powers that be and say, I can eliminate so much time and frustration and wasted, reagents in my lab by cutting out all these QC flags. And then we can save money clinically and help patients by reducing the number of M.U.R.s. But you're right, we need to have a way in that first 2 months when you're sending data in to give you the information you need to present to the C-suite.
Right, like it's a great opportunity to, use those 2 to 3 months of the free time to say, like, this is where we began and this is where we are now because of this use. And that's, that's the benefit to present.
Exactly. And that's one of the blocks in that, we quantify the improvements. So quantify the reductions in errors and QC failure. But you've got to go through that a couple of times in order to say, yes, we did realize those benefits.
Right.
Yeah, it would be really helpful if I could look at the slides on this presentation and the recording, Sherry, if you have one.
Okay.
And then play it for myself a couple of times until I can start to talk that vocabulary, if you like. You know, 'cause
Okay.
this is revolutionary stuff. There's no doubt about that. And
Yeah.
you know, we're the kind of the pilot group.
That's true.
Yeah.
Exactly. We're the pioneers, or we're not even the pioneers, we're the explorers.
Yeah.
You know, that they're leading the way but it is a better place to be. I'm sure of it. I've worked my life with this vision in mind,
Yeah.
and now the technology exists to bring it to life. And I'm
Yeah.
so excited to see it happening, to have the team at Elevate QC that are willing to, you know, put a business around this and create the software. And it's going to be exciting times ahead, and you guys are so pivotal to this. So that's our time for today, but let's move ahead and make this happen. I really appreciate you being here, and we'll get that recording and the slides out to you.
Amen.
Thanks so much.
Thank you, guys.
Thanks a lot.
Thanks, everyone. Have a good
Take care.
day.
Okay, bye-bye.
Thanks, everybody. Bye.